Hello everyone. In this video we're going to be solving a differential equation. We have dy over dx equals the square root of x plus y, and we're going to be solving for y if we can. Now this might look like a regular problem, but I promise the results will be pretty interesting. Do you want to see what the solution looks like? Here we go. Alright, so let's see how we can get something like that. So we have a simple looking equation, dy over dx equals the square root of x plus y. Okay, so for these kinds of equations, most of the time we use a method called substitution. You knew that, right? So we're going to go ahead and call x plus y something. How about calling this z? Y is a function of x. X is a function of x, so x plus y is also a function of x. In other words, we can talk about dz over dx, right? And that's something that's going to come up. But before that, let's go ahead and write this down. Z equals x plus y. Differentiate both sides with respect to x. And I'm just going to, for now, let's just, represent this with z prime. And then later on we can use the d notation. And the derivative of x is just going to be 1, and the derivative of y is y prime. Now our expression was given in terms of y prime, and now we're going to go from y to z. Okay, that's going to be our new variable. Since we do need y prime here, because that's what dy over dx means, let's go ahead and isolate it. Y prime can be written as z prime minus 1. Awesome. We're ready to plug in everything. Replace y prime with z prime minus 1. And replace x plus y with z, so that gives you square root of z. And then add 1 to both sides. And then replace z prime with dz over dx. Now, the reason why we do that is because we want to turn this into a separable differential equation. This is, in fact, a separable differential equation because we can separate the variables. This is where the fun part starts. First of all, let's bring this root z plus 1 to the left hand side, put it underneath here, and then multiply by dx. So different variables on different sides, we can go ahead and integrate. That's what's cool about separable differential equations. You can immediately integrate and hopefully get the answer. But guess what? Right hand side is easy. This is just going to be x plus c, right? C being a constant. But the left-hand side is not that straightforward. But don't worry, it's not too bad. So for the left-hand side, we're going to go ahead and use u substitution. Okay? So square root of z, set it equal to u. And then something interesting happens. Square root of z equals u. And then square both sides, z equals u squared. And then d both sides, dz, which is the derivative obviously, times the differential thing. Anyways, dz is equal to 2u du. And this is the fun part. If it's your birthday, happy birthday to you. Anyway, so that's dz, and we can go ahead and plug in everything. Dz will be replaced with 2u du, and square root of z is going to be u, so it's going to be u plus 1. Now, how do you solve something like this? This is a rational expression. Should we do partial fractions or polynomial division? No, none of that. I mean, you can do polynomial division, but there's absolutely an easier way to handle it. It is, again, division, but a little easier. Notice that 2u is 2 times u. So if we divide these two polynomials, the quotient would be 2. So we can kind of write the numerator as, in other words, I'm trying to manipulate this. We can write this as 2u plus 2 minus 2 all over u plus 1. And the goal behind this is basically to get a 2 from here. Because remember, I told you, if you double u, you get 2u. Not double u, but you get 2u. So from here we get this. 2 times u plus 1 divided by u plus 1 minus 2 over u plus 1. U plus 1 cancels out, and we are left with 2 minus 2 over u plus 1. Awesome. And if you make a common denominator, you will get the original expression. So we're going to integrate this. How do you integrate something like this? Easy, right? If you integrate 2, that's going to be 2u. I mean, what can I do? It's for u or 2u. It just comes up. And then this one is actually ln. So we can write it as 2 ln u plus 1 in absolute value, but I don't like using the absolute value. Just assume that this works. Okay? Wait a minute. What is this equal to? It's equal to the right-hand side, which is x plus c. Remember that? So we're going to set this 2u minus 2 times ln u plus 1 equal to x plus c. Remember, that came from the integral of dx, right? Cool. Now, we're not done with the cool stuff yet. Let's go ahead and divide both sides by 2, and it's going to give us u minus ln u plus 1 equals x plus c all over 2. Great. Now we have to back substitute. What is u? What did we call u, right? Square root of z. So let's go ahead and replace u with square root of z, and it's going to be square root of z minus ln square root of z plus 1 equals x plus c over 2. But wait a minute, where does z come from? What is z? Well, z is x plus y, so we have to back substitute one more time. So it's going to be the square root of x plus y minus ln square root of x plus y plus 1, so on and so forth. But wait a minute, the issue here is y is not by itself. Can we write y in terms of x? In other words, can we isolate it? Yes, we can. But let's go ahead and stick with the z notation for that, because it's going to make things a lot simpler. Not a lot simpler, but it's just going to simplify the process a little bit. So let's go ahead and work on this, and remember, z is x plus y. Okay? Cool. Now here's what we're going to do. If you divided both sides by 2, because I wanted to get the root z without a coefficient. And now here's the funnest part, in my opinion. Since we have an ln, we're going to do e to the power both sides. Let's do it. So we're going to put an e here and e here. Make sense? And then, of course, this is a subtraction of exponents. That just indicates division. So we can kind of write it as e to the power root z divided by e to the power ln root z plus 1. Make sense? And then, of course, that is equal to e to the power x plus c divided by 2. I could probably move this a little bit so it's not cut off like this. Here we go. Now, what can I do with this? Well, I have e to the power ln something. Does that look familiar? Yes. E to the power ln something, let's just call that s, is s. Great, something. So this becomes square root of z plus 1. In other words, this turns into e to the, I don't know where the x come from, e to the power square root of z divided by square root of z plus 1 equals e to the power x plus c divided by 2. Awesome. But again, we're going to make it awesomer. Okay, ready? So we have e to the something and then divided by something plus 1. Doesn't this remind you Lambert's W function? When we looked at the result from Wolfram alpha, it had Lambert's W function in it, right? Remember that complicated expression, which I could probably show you one more time at the end. So we're going to need to turn this into something like t e to the t. Can we do that? Sure, absolutely. Here's what we need to do. We have e to the power square root of z divided by square root of z plus 1. So we probably need to move things around a little bit, like reciprocate both sides. So like this, flip and flip. And then on the right hand side, when you flip, you're just going to negate the exponent, because that's what 1 over a to the power n is, right? That's a to the power negative n. You know that, hopefully. Now, why did I do this? Because if I keep the root z at plus 1 at the bottom, I can't turn it into t. But if I put the e to the something at the bottom, I can always change the exponent and make it e to the t. Make sense? Okay, that's a critical issue. And now we're going to need square root of z plus 1 though. So let's go ahead and do this. Multiply both sides by 1 over e. That's going to bring in an extra e here, which is going to give you, after adding the exponents, e to the power square root of z plus 1. Aha, I almost got my t. And of course here, this is just going to bring in an extra e to the power negative 1. So you can kind of write it as negative x, here, e to the power negative x minus c over 2 minus 1. And of course, you could also write it as minus 2 over all over 2. Anyway, same idea. Now, let's go ahead and negate this now. We're going to write it as e to the power negative root z minus 1 equals e to the power negative x minus c over 2 minus 1. So far, so good. Are you with me? Okay, great. We're almost done. Let's go ahead and negate, like multiply both sides by negative 1 because we do need t here. That's my t. So after multiplying by negative 1, this is just going to be, I should probably just write the answer, negative root z minus 1 times e to the power negative root z minus 1 equals negative e to the power negative x minus c over 2 minus 1. The negative is only going to be in the front. And now I can do Lambert's W function on both sides, and hopefully we'll get the answer. Okay? Let's see. This equal sign does not belong there. Let's put it here. Okay. Now, that should give us the negative square root of z minus 1, because if you apply Lambert's W function on t to the t, that gives you t, remember? And this is going to be Lambert's W negative e to the power negative x minus c over 2 minus 1. And then guess what you're going to do? You're going to add 1 to both sides and then square. Obviously, you're going to get the square of a sum, which is going to give you exactly what Wolfram Alpha shows, which was a little surprising at the very beginning, right? You probably weren't expecting something like this, but that's basically what it is if you look at it very carefully. By the way, that was in terms of z, right? Was it? Let's go back and check it out. Yes, we need to replace z with x plus y, and that is actually going to explain where the extra x comes from, because when you square this, you're going to get x plus y without a minus sign, obviously, and then you're going to subtract x from both sides to isolate the y. I'm going to leave that as an exercise, and you will get this as a result. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.